I am rather tired. I'm tired because I teach trigonometry at 7:45 a.m. I had to give a presentation at 11, and I had to stick around campus until 4:15 for a colloquium talk on a rather interesting subject. I'm really glad I went. But long story short is I didn't get home until real late, and now I'm kind of dragging. But I really wanted to make a video because it is Leap Day, and I wanted to have a video on the channel that was dated February 29th. I don't know, that might be weird, but it doesn't really matter. So what video did I decide to make? Well, I wanted to talk about Fourier analysis again, because last semester I took the first course, the first, section of Fourier, and now I'm taking the follow-up section, so technically it's Fourier 2. And it's graded, the way we're graded is the same as it is in the first semester, except the questions that were unsolved in the first semester carry over until this semester, which is the problem that I am going to present in this video. So this problem, I've been dragging my feet in Fourier 2 this whole semester, because normally I get done with the homework pretty early. You only have to do 5. But the reason I'm dragging is because I've taken on a lot of personal projects, like the graduate student interviews, which the last one will be recorded tomorrow, and then I just have to edit the other 3 that haven't been uploaded to the channel. And then after that, I've kind of sort of started the measure theory series of videos, which I did not forget about. It's just, finding the time to do it is, I probably should not have mentioned it at the time I did, but whatever, can't go back in time. But I have started taking notes over what those videos are going to look like. I'm going to probably make a follow-up video about like what to expect for that, but I don't want to talk about it just right now. The point is that I've been really busy. I've been meeting with my advisor. I've been doing all that stuff that I came up here to do in the first place with research. And unfortunately, homework kind of fell on the back burner, or was pushed to the back burner, whatever that saying is. So I did this problem. This is problem number 17. I started it last semester, did a lot of work, did not get credit for it because I didn't finish it. And instead of finishing it up, I kind of ignored it and started doing other easier problems. And usually when someone fails to do a problem at the board, if they've made significant enough progress on it, they kind of get to keep it, unless, someone else wants to do it and it's been a really long time. But that's generally kind of how it goes. So I finally decided to sit down and write up the solution to problem 17. I presented everything I'm about to show you with the exception of one tiny thing, and I'm going to explain it when I get there. All right, so enough talking. Let's look at the math. What is question 17? So question 17 says f is an L1 one-periodic function defined over the interval -1/2 to 1/2. And we want to prove that f is real analytic if and only if there exists a positive constant c such that the absolute value of f hat n, so that's the Fourier coefficient, absolute value of Fourier coefficient grows like, or I should say decays, like e to the -c times absolute value n. Okay. So it's an if and only if. So we need to do both directions. And just for simplicity, we denote in the class that t is that interval from -1/2 to 1/2. And I like doing left to right instead of right to left first. It's just a thing that I've always had since I started proofwriting. All right, so if we assume f is real analytic, then what does that mean? So this is the definition that we use. For any x0 in our interval t, there exists a radius r0 dependent upon x0, such that the series fx equals, and then you can read what it says here, converges, which I did not write that word. I really needed to write that word. In fact, it's going to bug me if I don't. Converges when absolute value x minus x0 is less than r0. So it's just a Taylor series expansion about x0. And then I claim that there exists an r positive such that f extends analytically to some big F on an open neighborhood of the real line, which I denote UR as the set of all z equal to x plus iy, where the modulus of y is less than r. So it's a strip. picture the real line, and then you have a strip of radius r around it. And I put a star here because this was a lemma that I was using that I did not have the proof of, and this is kind of the problem that I ran into. Now, this statement is true, but he wanted me to prove this statement in order to finish, and I didn't have enough time, or I want to say brain power, to solve it in that moment, because a lot of stuff that I had written up here, I should be, somewhat honest here, because I did find a majority of the solution on Stack Exchange, but the solution was missing a lot of details that I had to fill in. And when I was presenting this at the board, he was nitpicking pretty much every step, and I didn't have those details written out, so I had to do it up at the chalkboard. And it took me a long time, but I ended up, if he allowed me to use this for free, I would have been done, and I would have gotten my credit. But because I didn't have this one line proven, I didn't get credit for this problem. But I want to return to this at the end. So here's the equation for the Fourier coefficients, and this is the Fourier series that corresponds to it. You can see how it's defined here and there. Some textbooks will put the negative here and the positive here, but it's just a sign change. It doesn't matter too much. And now we consider the analytic function on the neighborhood UR. So this is big F of x times e to the 2 pi I n x. It is analytic because this is analytic and this is analytic. If you multiply two analytic functions, you get an analytic function. And then we set c tilde, which is just some constant, to be the following. So I'll let you read it. I won't read it out because you can read it yourself. But we know that c tilde is finite because f is an analytic function, so we know it's continuous. The absolute value of a continuous function is continuous, and it's over a compact interval. So you know it attains its maximum. So you know that the integral is bounded, so we can find a max value ranging over this set here, or these y values. So all I'm saying here is that c tilde is a finite number. And now you consider the contour gamma. So the contour gamma is the boundary of this set. And what does this boundary look like? It looks like the following contour that I've drawn here. And we're going to integrate with positive orientation, which means that we're going to integrate in the directions of the arrows. Okay, so what next? So we want to first consider the case where n is a non-negative integer. So what does this integral look like? Well, the Cauchy-Goursat theorem says that if we integrate this function, which for shorthand notation, I'm calling it fn tilde, if we integrate this function over gamma, which is what I've named the contour, you'll get 0. And we can bust up the integral into 4 pieces, which I've labeled bottom, left, right, and top. So this is the integral over the bottom of the box, the left side of the box, right side, top side. So you can see, I know it's a little bit informal, but it's okay. Bottom, right, top, left. So we're going to integrate that function over those pieces, and my claim is that the integral of the left plus the integral of the right of this guy will equal 0. So this is something that I had to do up at the board. But it's okay. I've had complex analysis. I should be able to do this. So if you're on the right side, your real value is fixed at 1/2. So when I plug in z on that right side of the box, or the contour, your z becomes 1/2 plus iy. So I put that wherever I have my z. And I notice that if I distribute the 2 pi in over iy, then I can pull that part out. Well, no, sorry. If I distribute 2 pi in with 1/2, I can pull that out, which gives me this e to the pi in. And why did I get a negative? Oh, because of never mind, I see why. So if you pull that out and I want to rewrite dz in terms of dy, it just becomes I dy, which is where this I comes from. And since we're integrating with respect to y, we're letting y range from 0 to r/2 because that's what it looked like on the box. So we're integrating from down here up to up here. So we're integrating from 0 to r/2. Okay, so this is my first integral for the right side of the box. Now what about the left side? So on the left side, you have a similar story, except your 1/2 becomes negative. And if you, again, if you multiply this out and then pull out the part independent of z, you should get e to the negative pi I n. And when you rewrite dz in terms of dy, you'll have negative I di, or dy, which is where this negative I comes from. And so we make two important observations. First, which is written here, big F is one periodic on T, because little f is, which means that these two values are the same, because negative 1/2 and 1/2 are separated. Their difference is 1. And we also know that e to the negative pi I n is the same value as e to the pi I n. Just think about what your unit circle is doing. So since these values are the same and these values are the same, when you add these two together, they will cancel and you'll get 0. So this was a question that he had for me when I was up at the board. Why does this equal 0? So we did that. Now, we're ready to estimate the Fourier coefficients in absolute value. So if we take the absolute value of the Fourier coefficient, we substitute in just with the definition of what I'm using for Fourier coefficient. And then we replace x with x plus IR over 2 in for x. I'm using this. The reason I tried doing this without justifying it, and when he asked me, he was basically asking the question, why is this true? Because this is true, we're allowed to make this substitution down here. And then, if we multiply 2 pi I n with IR over 2, the i's will become negative 1, the 2's will cancel, and then we can pull out the constant, which means we have e to the negative pi Rn on the outside, and then everything left over here. And now we want to get an upper bound for this guy. So if we just push the absolute values in, we'll have absolute value here, here, and here. But this guy has modulus 1 because it's a value on the unit disk. So it will more or less disappear when we, when we push in the absolute value. And then what about this guy? Well, this guy has to be bounded above, this whole integral, when I push in the absolute value, has to be bounded above by c tilde, because c tilde was supposed to be the maximum of integrals that look like that type. So when we put in c tilde, what do we have? We have this is less than or equal to c tilde e to the negative pi Rn, which is of the type, which is big O e to the negative c absolute value n. And this is just for the case where n is a positive integer, which is fine. If you want to argue for n negative, then all you have to do is rewrite essentially the entire, argument that's on this page, except you want to use a different contour, and the contour that you want to use is the bottom box, where you have the boundary of t cross negative r over 2, 0. So it's this shape except on the bottom. And I didn't write up those details because it is kind of the same calculation and it just kind of wastes time. It was obvious to the class, so I didn't end up writing it. And that concludes the first direction. What about the second direction? So we assume that there exists a C positive such that the absolute value of f hat n is equal to big O of e to the negative c absolute value n. And we want to show that f is a real analytic function. So the first thing we do is we define a complex valued function, gz, to be the sum of the Fourier coefficients of f times z to the n for integers n. And this gives us a Laurent series. And we want to see where gz converges. And what I do first is I split it up into two pieces. So the first piece, S1, only considers non-negative integers, and S2 considers negative integers, which I've written over here. I have these swapped, but what you can do instead is, instead of doing negative integers, you can rewrite this as n equal 1 to infinity of f hat negative n times z to the negative n. There's no real reason to do it that way, it's just I liked it. So the question now becomes, if I know where these two series converge, then I know where G will converge. So where does S1 converge? Well, we can use Hadamard's formula to find the radius of convergent, which means that mod Z has to be less than R, which if R is the radius of convergence, this is what Hadamard's formula tells us. We have 1 over lim sup nth root of mod f hat n. Man, this problem took a long time to write. What is this how much did we use in this? And it's not over too. We still have that one thing at the beginning I didn't prove to the class. So, whatever. So if you substitute in what we know about the growth of f hat, it's supposed to look like something like c sub 1, which is just another constant, times e to the negative c mod n, modulus n. So if we push the nth root over both of these two factors, that modulus n will cancel, and we'll have c1 raised to the 1 over n power times e to the negative c. And if you take the lim sup of this expression, this doesn't do anything, and this guy will tend toward 1, so it'll more or less disappear, and we'll have 1 over e to the negative c, which is better known as e to the c. So we found a radius of convergence for S1. So if S1 converges on this guy, then by definition of S2, we know that it will converge outside the circle of radius e to the negative c. So S2 converges here, S1 converges here, and S2 converges here, which means that G will converge on the annulus given here, more or less the intersection of these two. So because GZ converges, we know it's an analytic function on the annulus, and it's an analytic extension of f, because we know that f of x is just equal to g of e to the 2 pi I x. And you can see this by saying, okay, take this guy, this weird thing, and plug it into G. If you plug it into G, wherever I defined it, here, you'll have e to the 2 pi I n x, which just looks like the Fourier series of f. So if this is the Fourier series of f, then we can see that f has to be a real analytic function on our interval negative 1/2 to 1/2. I hope I did not miss any details. I feel like there's something missing here, but I don't really think I left anything uncovered when I wrote this up on the chalkboard. I'm sure someone will catch it. But yeah, this was a beast of a problem. And I did not get credit for it because I was missing the line with the star in it. So after class today, I went back to my office and I was trying to see if I could come up with something. And I believe he told me, I worked on it a little bit and showed him what I had afterwards, and he says I'm on the right track, but, that could mean a lot of things. And so this is my proposed idea of what to do. I'm not guaranteeing that this works. I'm still thinking about it, but hopefully I'm on the right area. So what do we know? So if we take any alpha between negative 1/2 and 1/2, we can find a radius, r alpha, depending upon that point chosen, such that the power series, G alpha, defined as such. So it's just a power series expansion centered at alpha, except now we have z instead of x here. This series will converge on the disk mod z less than r alpha, which I denote with br alpha alpha. Just a ball of radius r alpha centered at alpha. So you have a bunch of balls for alpha between negative 1/2 and 1/2. And because we know that T is compact and T is a subset of all these balls, we know that there exists a finite subcover. So that's what I'm essentially saying here. We can find a finite family of balls where their union covers T as well. And for simplicity, I was using a lot of notation here, so like going back and defining things. But I call this union, this finite union, B tilde, and this is more or less what B tilde looks like. So you can see the curly line that I've drawn is the domain of F. It is one periodic, but it's defined on the whole real line. And between -1/2 and 1/2, I've found this finite collection of balls of different radii, and I can cover it with it. And I'm interested in studying the intersections. So if Z is a complex number that is in the intersection of two balls, which, again, I get nuts with the notation, but bear with me. If Z is in the intersection, like right here, if Z is in this football shape, then what? What does the identity theorem tell me? It tells me that the two analytic functions, g alpha k and g alpha k prime, are equal to one another for any Z that's in that intersection. And then what does the identity theorem tell me? It says that if f and g are two analytic functions on a same domain, and f is equal to g on some open subset of that domain, then f is equal to g on the whole domain. So what I want to say, and I'm a little bit scared of this because I think I'm missing something, is that in this ball, for example, we have g alpha k. In this ball, we have g alpha k prime, and they agree with one another on the football shape, which means I want to say that they're the same analytic function on the union of those two balls. So if I can say that, then I can play the same game with this analytic function that's on the union of these two balls with this ball, and play the exact same game so we know that they're the same across the three balls, and then you just keep going down the line until you've done it for all balls. So you end up with one analytic function across all balls. And then, my God, you create your strip. And one thing I was saying is like, okay, just look at the infimum of the distance between the interval t and z, where z is, that should be complement, not b tilde, the complement of b tilde. So you look at the smallest distance that you can create from a point taken on the interval and a point taken outside b tilde here. You look at that smallest possible distance and you cut it by a really small number. And if I set r equal to that, then I'll get my strip ur, and then I want to say that g is my analytic extension f in the complex plane. I'm a little bit scared about the argument I gave here because I feel like I've missed something, because I don't know necessarily that this is saying that I can say that these two functions coincide on the union of these two balls just yet. I feel like there's something else that I need, because I don't know. When I was talking to him about it, it sounded like I needed some prior knowledge about F. Like it's, well, I mean, the only thing I know about it is that it's L1. But I don't know. I guess I'll think about it some more. If you see anything that's obvious that I'm missing or I've gotten completely wrong with this, feel free to comment. But this problem was not easy. I thought it was going to be easier than I originally, when I first started working on it. But props to Math Stack Exchange. They've saved my butt so many times. But anyway, too long a video. Thank you for watching. Fourier analysis strikes again. And I'll see you in the next video.